Let's do some trig integrals. Page 11, probably. Nope. 12? Yes. If you're experiencing deja vu from this chart, it's actually not deja vu, it's the same chart. It's the same exact chart. We're just going to look at the other side. So what I want to point out here is that we can only integrate the results of doing the derivatives here. So like what's missing from this is the integral of, not secant squared, that's not missing. What's missing is the integral of secant. What's missing is the integral of tangent. Because those aren't results from our derivative table. We will learn how to integrate tangent. I'm not sure if maybe it's just earlier. I need to get back in the zone, but I don't think I know how to integrate secant off the top of my head. Or I think it's just complicated. Yeah. So can only integrate the derivative results. I'm supposed to say yet. My pen is getting smaller and smaller. I've already had a lot of problems with these pens. Anyways, okay, so we basically need to be on the lookout for these derivative rules. And so that's why last class I was saying, hey, just memorize the derivative rules, focus on the left column. And for integrals, just think of going backwards because that's really all we're doing. And also, like I mentioned last class, when we do the integral of cosine, it's positive sign. But when we do the derivative of cosine, it's negative sign. Raise your hand if you think you're going to mess that up at least once. Yes, my hand's up too, and I do this professionally. Okay, so what helps me is to just think about the derivative rules. Derivative of sine is cosine. Okay, so if I'm going backwards, check your answer by doing the derivative. I'm always thinking about derivatives and less about integrals. Actually, a good analogy is derivatives are like multiplication, and integrals are like division. And mostly like they're opposite operations, but one's easier than the other, right? Multiplication's easier. And so if you think of like, 63 divided by 9. Well, I know 7 times 9 is 63. Okay, so it's 7. It's kind of like that. It's like thinking of the easier way to help you with the harder thing. It's just an analogy, but maybe you did that when you were younger, and now you get to do it again. So lots of U sub, of course. It's going to get crazy with U substitution. But as we scroll down here, so remember we can factor constants out. We just had our integrals unit, so it's a lot of these things should be kind of fresh. So I think, what derivative is cosine? It's sine. This is just 2 sine of x plus c. Now, once we look at number 2, and it's sine of 4x, we have something on the inside. So we could use u substitution. Whenever we use u substitution, we always want u to be the inside function. So u would be 4x. But I'm going to encourage you guys to avoid using u substitution on this because with something so simple, we really do want to think about, okay, this needs to be, negative 1/4 cosine of 4x plus c. And we need to account for that 4 on the inside. We need to account for if we did the derivative of that, it would be negative sine, and then we would do the derivative of the inside, so it's got to cancel out. You can check with u substitution, or you can check your answer by doing the derivative. I would say for simpler ones, we kind of want to just think about it and think about what needs to be up front. But if I was going to keep going with this u substitution, this becomes, you know, like I would say 1/4 du equals dx, and then we would have 1/4 sine of u du, and we would integrate that, and we would get negative cosine, and then we could resubstitute our 4x. But I would encourage you to try and skip that step. Let's do. I want to have you guys do. Numbers 1 through 9. Numbers 3 through 9. But we'll do it on a short timer here. Take 6 minutes, 1 minute per question. Ready, set, go. What's number 3? What'd you guys get? 2. What?
Sine 1.
Yes.
Plus c.
Plus c. Yeah. Because, and again, check by doing the derivative. It'd be 2 cosine 1/2 x times 1/2, so they would cancel out. Would there be any number out front for number 4? No, there wouldn't. But it's going to be negative, right? Negative cosine x plus pi over 4 plus c. That plus pi over 4 is not going to do anything in the derivative. The derivative of the inside is still just 1. Okay? What number will we have out front for number 5? 1/2, yeah. 1/2, positive or negative sign? Positive. Again, just check by doing the derivative. Derivative of sine is cosine. Positive cosine. Okay. It's positive, should be positive. What are we going to have out front for number 6? Positive 3. 3 cosine x pi over 3 minus x plus c. What's the best way to check? Do the derivative. So this would be negative 3 sine pi over 3 minus x times the derivative of the inside, which would be negative 1. Okay? Yeah, that's what we started with. Yep. Secant tangent, what do we get? Secant, yeah. So just recognizing that from the derivative rules list. Cosecant squared, what do we get? Yeah, negative cotangent. Because the derivative of cotangent is negative cosecant squared. And then number 9. 5 over 2 tangent 2x plus c. Yes. Yeah, we do the derivative. It's secant squared of 2x times 2. Cancels out. Okay, so just recognizing those rules going backwards and accounting for constants that are on the inside. Basically, you just have to divide by the constant that's on the inside, because when you take the derivative, you would multiply. So we're going backwards. Okay. There's some other random tricks like number 10 and 11. Those aren't from the derivative list until we change that to say 4 cosecant squared x using our reciprocal identity. And number 11, that's actually secant squared of 4x plus 1. And so now, oh wait, these are actually on the derivative list. That's actually going to get more difficult at the end of the year, because you're going to start to confuse this with natural log derivatives. So we will circle back to this, but for right now you have a more limited list to work from. So we would be able to do those. Okay, so let's just review the process for definite integrals. I know we just took a test on this, but I also haven't graded it yet, so I guess I don't know if you guys can do it or not. You know if you can do it or not. But if I integrate cosine, what do I get? Sine. So this would be sine of x evaluated from 0 to pi over 2. So our notation, remember, we get rid of the integral sign. We add in the vertical line there with our two numbers. we're going to plug in pi over 2 and subtract what we get when we plug in 0. And so this just becomes 1 because it's 1 minus 0, but mostly just to review the process, even though it was really recent. This is our good old fundamental theorem of calculus, part 1. I want you guys to try do 13 and 14. Okay, let's talk about these because number 14, there is an easier way to do it, but it's looking like we're having some trouble with that one. So number 13, just to check it, we would get negative 1/2 cosine 2x evaluated from 0 to pi over 6. Is that right? Did I do that right? Okay. So when I do again, when we have a constant like that, I like to just put it on the outside and worry about it later. So this becomes cosine of pi over 3 minus cosine of 0 inside. And then cosine of pi over 3 is 1/2 minus 1. So this becomes negative 1/2 times negative 1/2, which is 1/4. Do you guys get that? Okay. There is an easier way to do number 14, but it's not a way that's going to consistently work. We can replace this with 1/2 sine of 4x using the double angle formula, and then it's a lot easier to integrate because our double angle is sine of 2, I'll just say theta, equals 2 sine theta cosine theta, and so our theta in this case is 2x, so we would double it, make it 4x, and we're supposed to have a 2 out front, so we need a 1/2 to account for it. So that will make integrating this way easier, but it won't work for, if you look on the next page, it won't work for something like that, it won't work for something like that, or that. So what we are going to need to do, what we're going to need to be able to do is U substitution. And this is one of those cases where I definitely would use U substitution. So turn to your neighbor, what should we use for U? What do you think? And also think about let's go back to when we first talked about integrals. What would we have needed to take the derivative of to get something like this? What kind of, without using any double angles or anything, even look back to last class's notes. What kind of questions have results that look like this? What functions' derivatives look like that? You guys see what I see? Maybe? Yeah, so we got that kind of result. If I simplified this, this would be like 4 sine 2x cosine 2x. So we got that kind of result by taking the derivative of sine squared, because we basically had to do the chain rule. We had to do the power rule on the outside, move the 2 down, but then, so that's sine to the first power, then times a cosine for the derivative of the inside. So that's the function that basically we're going to get as a result, some sort of sine squared or cosine squared. We could pick either one, actually. But that's our end results. What page am I on? This page. Yes. So when we're doing u substitution, it's not going to be helpful to do u equaling 2x, because when we do that, we have to integrate cosine u sine u. And that's kind of the problem that we are having with this, or we're having. It's like, what is the integral of that? Like, how do we integrate that? So what we're going to decide here, it's going to be more obvious in other questions, but it's hard because they're both to the first power. What we're going to decide here is we're going to pick either sine or cosine to be the inside function, and one of them to be the derivative of the inside. So we're going to pick, let's just pick sine of 2x. And then what's the derivative of sine of 2x?
2 cosine 2x.
2 cosine 2x. Okay, so we're going to need like a 1/2 du equals cosine 2x dx. And we're also going to need to change our bounds. So what does u of pi over 4 equal? Yeah, it's 1, because it becomes sine of pi over 2. And then u of 0 is 0. So when we substitute, here's what we're going to see. We're going to see the integral from 0 to 1 of, here's 1/2, just u du. Udu. The cosine is 1/2 du. So we're replacing cosine 2x dx with 1/2 du, and we're replacing sine of 2x with u. Because what this is revealing to us is what we actually have to do to integrate, which is the reverse power rule. So we're actually not really doing a trig integral, we have to power rule this. Because remember, we saw already, our end result is going to be something like sine squared of 2x plus c. Where if we were going to do the derivative of that, it would be 2 sine 2x to the first power times cosine 2x, this one times 2. Okay.
Why do you change the bounds on this one and not the last one?
I didn't use u substitution on the last one. Yeah, anytime we do u substitution, we have to change the bounds, but only when we do u sub. So when we integrate this, it's u squared, 1/2 u squared, evaluated from 0 to 1. And so the answer is just 1/4, because I plug in 1 and then subtract 0. But if I wanted to break that down into steps, it's 1/4 times 1 minus 0. That's just 1/4. Now, this would also work. This works if we pick, this is a weird one, so we could also pick u to equal cosine of 2x, and it would work. And we would basically get like negative 1/4 cosine squared 2x as our function, as our integral. So it would also work that way. So that's why this one's trickier. Some of them are going to be more complicated looking, but also easier to figure out what we're supposed to do with the u substitution. So go to the next page. I want you guys to look at number 16 and see if you can figure out what u is supposed to be and if you can substitute everything in correctly. Okay, what do you guys say for u in this one? What do we think? Sine squared. Other options for u? Cosine. Other options? Cosecant squared. Other options? I have terrible news. It's none of these. Okay, so, yeah. Sine theta, yes, that's correct. It needs to be sine of theta. Okay, so when doing u substitution, because now it's all getting more complicated now, which is kind of, that's life. But when we're doing u substitution, what we are basically trying to integrate is this. And if we throw back all the way to the beginning of Unit 3, what we want to be on the lookout for is an outside function, an inside function, and the derivative of the inside. And so we're trying to identify those things when we're integrating the chain rule. So in this case, our outside function is like f prime, and our inside is g, and derivative of the inside is g of x. I'm trying to actually pull up the notes from Unit 3 right now. But our goal when we do u substitution, this is the one that becomes u, the inside function. Okay, yes, here it is. Wait. Okay, yes. Throw back to Unit 3. What we're looking for is an outside function, inside function, and a multiple of the derivative. So the inside function is what we make u. I don't know if me pulling this up is helpful or not, but it's all, the page is all shifted underneath it, which is crazy. Whoa. There we go. So when we're looking here, what we want to see is we want to see this. And so do you guys see the function that we could call the outside function? Okay. Well, I would just say it's 1 over x squared. Yes. Because there's a sine and a cosine. The sine is the inside function, and the derivative of the inside would be what? Cosine. So between all three of those things, we can map everything that's present here to one of those. That's what we're looking at. Outside function is just the -2 power on the bottom. What's inside the -2 power is sine of theta. And cosine is just what came out here. It's the g prime of x that kind of came out with the chain rule being done. So we always want to make u the inside function. And so u is sine theta. What's the derivative of sine theta? Cosine theta. Okay. And so we don't need to mess around with any constants. We have that. And so what we're integrating here is just 1 over u squared du. And so when we integrate that, it's just negative 1 over u plus c. Or negative 1 over sine theta plus c. Now, so actually, something we could do with this is we could, this is the same as cosecant, cotangent. And so we could integrate that to get negative cosecant. So there is an easy way to do this one, but that is not a consistent method, because if this is to the 4th power or the 5th power, we would need to use u substitution. We couldn't use any trig identities with that. Okay, I'm gonna put you guys into groups, and I want you to do 18, 19, and 20, and then we'll go over them. Also, let me just say, it's okay if this is confusing. This is like all of a sudden where calc gets really confusing, is once integrals get more complicated. As you practice it, as you get used to looking for the inside function, it will start to make more sense. So don't feel overwhelmed if suddenly it's like, wait, this just got way harder. Yes, it did. That's okay. You guys got this. Okay, I'm gonna give you guys a little direction here. In 18, we want u to be x squared. In 19, we want u to be root x. In 20, we want u to equal sine of x squared. Okay, guys, in the interest of time here, I'm going to go over these. So what I'm recognizing in 18 is outside function is sine, inside is x squared, and then x, that x there is a multiple of the derivative of the inside. So the actual derivative of the inside is 2x dx. We just have x dx. So we're gonna replace that with 1/2 du. And so this becomes 1/2 times the integral of sine of u, which just becomes negative 1/2 cosine of u plus c. And make sure you resubstitute in for x. We don't have to do that when we're doing definite integrals, but we do have to resubstitute when we're doing indefinite. Like when we're just evaluating between points, we can skip that step, but we have to do it for this. So for number 19, same thing, sine is the outside function, root x is what's inside. The derivative of root x is 1 over 2 root x. And we don't quite have that, we have just regular 1 over root x, so we need to multiply this by 2. So that we can replace this with 2 du. And then we have sine of u. So it's, again, negative 2 cosine u plus c, or negative 2 cosine root x plus c. Now, 20 is definitely the craziest one, because what's actually happening here is there's 4 functions. There's the cubed, the sine, the cosine, and the x squared, and the x. I guess there's 5 things that we're trying to identify here. But what we want to do is we want u to be like the first inside function. Because basically what we're working with here is like f of g of h of x. or h of j of x or something like that, we always want to pick like the second layer for u. Because when I do the derivative of u, this becomes cosine of x squared times 2x, which accounts for this cosine of x squared and that x right there. So the only thing I need to do is divide this by 2 to make it match. This would be 1/2 du equals x cosine x squared. So I'm replacing this with 1/2 du, and I'm replacing this with u. So it becomes u cubed, it's like neon Christmas colors, times 1/2 du. And our goal is to replace everything. Because really all this is like the power rule. Um, 22, 23 are good example questions to do for extra practice. I think the Delta Math questions aren't great. We'll have a review guide for you guys next time. Next class, we do have a quiz. It'll be at the end of class. And you'll get it back next Thursday for your test. Make sure you do your homework.